This short lecture is part of the course Introduction to Apache Spark APIs. We will see how the data frame APIs introduced in previous lectures in this course can be used for building and operating a data platform. So Spark can help you to build a data platform and operate it. Spark provides, with the data frame API and Spark SQL, powerful abstractions and a rich language for data preparation and data analytics. You can run data frame operations at scale using distributed computing. You can run on clusters, on Hadoop, or on Kubernetes with cloud resources. Spark can easily integrate with a large ecosystem. For example, you can use many file formats, Parquet, CSV, root of interest for physics. You can operate on several storage systems, Hadoop storage system, HDFS, S3, and other cloud file systems, EOS of interest for CERN. You can operate on external systems like databases, Elasticsearch, streaming, and also Spark integrates with table formats and systems that can do transactions like Delta, Iceberg, and Houdin. First step to build a data lake or a platform for data processing will be to ingest the files. Spark can help you there. There are various options. Actually, if you have bulk file sources, maybe you just need file copy methods into the storage system. If you're reading from a database, you may want to use Spark. There are also other tools, but Spark works very well with the JDBC data source to ingest data into distributed storage. Again, storage can be Hadoop, it can be a cloud file system like S3 or EOS if you're at CERN. Spark can also operate on data streams. We will see that in a separate lecture how you can do that. The data frame reader and writer APIs are key for operating with large data sets with Spark. And Apache Parquet is also a format that we will cover in this lecture. So Spark can process many file-based data formats. With the data frame reader, you ingest files or folders containing files, and all these files are mapped into a data frame, which is a table abstraction. And an example of format that is very useful for data analysis and ingesting large amounts of data is Apache Parquet. Here we see how you can operate on the Parquet data format. You will have the Spark session, typically called Spark, and then you operate with read, format Parquet, and load file name or folder name when you have a folder with multiple files in it. There is also a shorter syntax where you just do Spark read Parquet, and then the path. The Parquet reader in Spark has Partition Discovery. So partitions are defined through the file system. So the table abstraction that becomes a data frame becomes a folder in the physical reality of the storage system. And this folder can contain one or more files or can also contain subfolders. If you have subfolder with the naming convention partition column name equals value, this will describe a partitioning structure. This example here shows what I meant. So you'll have a table name, so a folder that contains the table, and then you will have partition 1 equals, let's say, value 1 with one or more files, which could be Parquet snappy compressed files. Then again the same partition column with a different value, and so on and so forth. And when we read with Spark, let's say we read Parquet, we just point to the upper level here, table name folder, and all the data will be read, including the partition definitions that are implicit by the folder structure. You can do print schema, and you will show the schema of the data that you've read, including the partition column. Data frame writer is the other side of these operations. That when you want to write out data, let's say you want to write that in Parquet files, and then there are multiple options that you may want to know. Here we will cover a few. For example, the possibility of reducing the number of partitions for the output, or also increasing the number of partitions with repartitioning. And these operations affects the number of concurrent tasks that will be used for writing, particularly if you coalesce, so if you reduce the number of partitions to small numbers, let's say to 1, you will only have one output file, but it may be slow if you have a large amount of data because only one task will be running. So the number of partitions defines the parallelism of the operation. Okay, let's see an example. You say you have a data frame after several transformations in your application. Then you may want to coalesce it or repartition if you want to create more partitions. And then you do write. So you activate the data frame writer with this. And this is the logical partitioning of the data, partitioning the folder structure that we discussed in the previous slide. And you can partition with one or more columns. And then you define the format. Let's say you want to use Parquet and define the folder name here. Other options that you have are repartitioning. And if you repartition on the same columns that you used in the partition by, you will end up with only one file in each folder of the partition defined by these columns. So this is a useful trick to compact when you're writing, particularly if you're writing with partitions. And then there are many options. An important one is compression. By default, when you're writing Parquet, you get snappy compression, which is a good compromise between compression, size, and speed. You have other algorithms as well. And then you can specify if you want the overwrite mode. This will overwrite the files or directory if it already exists. Very useful for testing. Could be dangerous in production because you may end up overwriting data that you need. So why would you want to use the Parquet data format? First, the most important part is that Parquet is a columnar format. There are also other columnar formats, but Parquet is quite used. And this means that data are separated by column. If you're only querying a few columns, you're only reading those columns that you're querying. Then there is encoding. Let's say you have repetition on the data. There's a value that is repeated for many, many rows. Parquet will encode this and will just write this value once, and then we'll use say some marks that the data is just repeated. And then you have a compression on top of it. Snappy compression, as I mentioned, is the standard one. Also other compressions available, including Z standard, which is a relatively new compression format and compresses more aggressively than snappy. Then data is stored with this schema, which is very handy. So you get column names and data types, so the full schema, in the Parquet files. Schema evolution is also supported. Also, Spark is optimized for using Parquet. By default, it uses the Apache Hadoop Parquet reader, but it has also an additional optimized reader, customized vectorized Parquet reader, which improves the performance of many of the operations when reading or writing Parquet. Another important point in optimization of Spark when using Parquet is that Spark can push down filters. Let's say you have a filter on a certain column. Instead of reading the data in Spark and then operating the filter at that level, Spark can push down the operation of the filter down at the level of Parquet when data is being read. And this optimizes the operation. Also, Parquet stores minimum, maximum, and count values of the data stored in Parquet at the granularity of the row group, which is typically 128 megabyte, and also at the granularity of the Parquet page, which is typically 1 megabyte. And Spark can take advantage of that by skipping reading data when we apply, for example, a filter with a value that is outside the minimum maximum value. And this improves the performance by reducing, in some cases considerably, the amount of I/O into the file. This works best when data is sorted on the column where we want to filter, so that this trick of using minimum maximum ranges at a smaller granularity of the page, say 1 megabyte, works better if we are sorting on that column. Also, recent versions of Parquet and also Spark using Parquet supports Bloom filters. So data formats are very important for the operations of data platforms. If you have large amounts of data, CSV may have large performance impact because you may have large data files and many of them, while Parquet is more compact and more suitable for analytics of large data files. So this brings us to the key learning points of this short lecture, is that the Spark ecosystem builds on data frames. Spark can run data frame operations and SQL at scale, integrating with several clusters, Hadoop and cloud, and many storage systems. Choosing the data formats is key for performance and availability. For many data analysis workloads, you want to have columnar data formats, and Apache Parquet is typically a good fit. And this ends this short lecture.